Resistors in series and parallel. It's a very important concept, how the resistors are combined in the circuit. They can be combined in series and as well as in parallel. We have discussed about capacitors also in the previous chapter. So similarly, resistor is one of the passive component. So how they are connected in series? In case of resistors in series combination, we are going to consider the resistors having resistance R1, R2 and R3. So these are the resistors having the values of resistance is R1, R2, R3. They are connected as shown. So this connection is said to be series combination. When the ends of these combinations is connected to a potential difference, a current flows through the circuit when the circuit is completed, and this is the direction of current flow. So the current is flowing in the clockwise direction, and whenever the current flows through each resistor, a voltage will be developed across each resistors. We know that whenever a current of I ampere is allowed to flow through a resistor, a voltage will be dropped across the resistor. So that is Ohm's law. V is equal to IR. Here the potential applied is V. Because of the different values of the resistors R1, R2, R3, the potential developed across the resistors also differs. So V1 be the potential developed across R1, and V2 be the potential developed across R2, and V3 be the potential developed across R3. And to be noted that since the value of current remains constant throughout the circuit, because the current has only one single path to cross all the resistors which are connected in the circuit, and therefore if there is a single path for traveling, the rate of flow of charges, which is called as current, remains constant. It is well known that therefore the current remains constant in case of series combination. Now here the applied potential is equal to V1 plus V2 plus V3. Hence the total potential supplied will be developed across each resistors as V1, V2 and V3. So the sum of these values will be equal to the total voltage. And according to Ohm's law, we know that V is equal to IR. This is the Ohm's law. And while substituting for V1, we had I into R1, and similarly for V2 we get I into R2, and similarly for V3 we get I into R3. And substituting the values here, we get IR is equal to IR1 plus IR2 plus IR3. So I is a common term, so it can be cancelled on both sides, and RS will be equal to R1 plus R2 plus R3. So it is very simple. When the resistors are connected in series, then the effective resistance will be the sum of the individual resistances included in the circuit. For example, if we have R1 as 1 ohm, R2 as 2 ohm and R3 as 3 ohm, so we have 1 plus 2 plus 3, that is equal to 6 ohm will be the effective resistance. So here when the several resistors are connected in series, the total or the effective or the equivalent resistances is the sum of the individual resistances. And also to be noted that the combination of this resistance RS in series, therefore I have written as RS. RS represent for series combination. So the total resistance in series is equal to 6 ohm, and this 6 ohm is greater than the greater value of the resistor included in the circuit. So from this we have the equivalent resistance will be greater than the greatest value of resistance included in the circuit when they are connected in series combination. Okay. So next, how to conclude. So this is the conclusion for series combination. If you connect the resistors in series, definitely the total value of the resistance will be getting added up. Okay. Now, in the case of parallel combination, so this is how we have to connect the resistors in parallel. Here, the ends of this resistance and this resistance and this resistance. So we know the resistor has two ends on left and right. The left end of each resistors are connected to the point A, and the right end of each resistors are connected to the point B. So this is the total voltage applied will be V, and the current applied, the current flowing through the circuit will be I. Since the current is flowing here as shown here, when the current enters this point, it has three different paths to travel. In the previous case, it has only one single path. Here it has three different paths to travel. Therefore, the current is divided as I1, I2 and I3. As such, we have to look at a water flowing through a canal. When it is when the canal is divided into three ways, three parts. If the canal has three parts, the water will flow through all the three parts. So in a similar way, the current is flowing through all the three parts, and we know Ohm's law, V is equal to IR. So here this current I1 is flowing across this resistance and comes to the point B, and I2 is crossing this resistor and reaches the point B here, and I3 reaches this direction and it reaches the point B here, and actually the total current will be again flowing through this circuit. So this is how the parallel combination works. Okay. Since the ends of each resistors are connected to A and B, the potential drop across each resistor will be constant. In the previous case, we have found that current is a constant. Here the potential developed is a constant. So here V be the potential developed. So if the potential developed is V, for example, if this is the potential applied here, let V be the potential applied here. So this potential V is it should be a constant, because the positive ends are connected to A, and all the left end of the resistors are connected to the same point A, and therefore again the negative end is connected to B, and all the right ends are connected to B. So therefore this point B and this point A are at the same potential V. Therefore the voltage drop or the potential drop across each resistor will be a constant. So V is a constant in this case. Rearranging the equation, I is equal to V by R. So I1 is equal to V by R1, I2 is equal to V by R2, I3 is equal to V by R3. So this is how we can write. And here V is a common term. So we get 1 by Rp is equal to 1 by R1 plus 1 by R2 plus 1 by R3. And when several resistors are connected in parallel, the sum of the reciprocal of the values of the resistance of the individual resistor is equal to the reciprocal of the effective resistance. So here we have to consider the reciprocal term. Okay, and in this case, the effective resistance will be smaller than the smallest value of the resistors included in the circuit. So in the previous series combination, we have discussed the effective resistance will be greater than the greatest value of the resistance. So here, if we consider the same values 1 ohm, 2 ohm and 3 ohm for these respective resistors, then here the effective resistance will be less than 1 ohm. So we have to conclude that when the resistors are connected in parallel, the effective resistance will be always smaller than the smallest resistance included in the circuit. Okay. So thank you, and keep on watching, and don't forget to subscribe. Let us meet in the next concept.